Hello and welcome to another lecture in our course on formal methods. And today we're going to talk about causes and correlations. In philosophy in general and in philosophy of science in particular, there's a long-standing debate about what causation is. One of the starting points of this debate is the work of David Hume and David Hume's apparently quite simple and innocuous definition of cause. Um, this is what Hume says. We may define a cause to be an object followed by another, and where all the objects similar to the first are followed by objects similar to the second. Now, this has been called a regularity account of causation. Um, the idea is that causation is an invariable association between types of events. Hume uses the words constant conjunction. So one thing is always followed, one type of thing always being followed by another type of thing. These kinds of accounts have problems. Um, First of all, in many cases, event types are not invariably followed by one type of effect. For example, we say that smoking causes cancer, but it's not the case that smoking is always followed by cancer. And this is a feature of many causal relations that are of great concern to us, that they are not invariable associations. We also now have a worldview that is at the very basic level indeterministic. Namely, we think that the laws of nature themselves are probabilistic in nature, that there are events that are not invariably followed by other types of events, even if you know everything that is relevant and that's going on, there is only a probability that certain types of events will occur. That's the reality that how it is described by quantum physics. And so if we still want to speak about causation on this level at all, then the regularity view in Hume's terms will not do us any service there. And another problem for regularity accounts is spurious correlations. Consider this example. Whenever the mercury column in my barometer drops below level so and so, a storm occurs shortly thereafter. Well, this may very well be the case, but it doesn't mean that the dropping of the mercury column in the barometer is the cause or a cause of the storm. Now, the first two problems, the lack, the fact that causes are not always invariably followed by their effect type events, and the indeterminism problem, those are both problems that show that invariable association between types of events may not be necessary for causation, whereas the last point, the spurious correlation point, seems to show that invariable association between event types may also not be sufficient for causation. So these and other problems, this is just some of the most pressing problems concerning the regularity account have moved many philosophers, in particular in more recent times, to try out other accounts, alternatives to the regularity account, to seek their luck for analyzing causation in counterfactual dependence, for example, which is approach of David Lewis. Causation is based on counterfactual dependence between events, so it's not relevant, not so relevant that B always happens when A happens, but what's relevant is that B would not have happened if A had not happened. That's one approach. There's a physicalist account based on the work of Wesley Salmon and Phil Doe, where causality is a feature of certain kinds of processes, namely those processes that transport conserved quantities such as energy, momentum, and so on, and certain kinds of interactions between processes, namely those that involve an exchange of conserved quantities. So we use some very basic concepts of physics to distinguish causal from non-causal features of nature. And there are manipulability accounts, um, most strongly associated with the work of James Woodward, where causes are circumstances that one can intervene in to manipulate the effect. So intervention becomes the core concept for understanding causation. All these alternative accounts also have their problems and shortcomings, and I'm not going to discuss any of them. Um, I'm I'm rather going to focus on something else completely, because besides all these attempts to find alternatives to the regularity approach, to the old Humean approach, there has also been the approach to hold on to regularity ideas and to save it by means of the concept of probability. And this is sometimes called the probabilistic approach or the probabilistic theory of causation. In order to do that, philosophers of science have developed some ingenious formal methods, and that's why it's interesting for our course. That's what I'm going to talk about this topic at all within this course. And the methods developed by philosophers within this approach that is basically directed at saving a regularity type of approach to causation, these methods turn out to be very important and very helpful for thinking about causation, even if you don't belong to this camp, even if your agenda is not to save the regularity account of causation, even if you just want to think about and understand causation. The formal methods that probabilists have been developing are still extremely interesting. Most importantly, these methods have also turned out to have considerable practical scientific value for identifying causal relations. That is, for really finding cause-effect connections within, for example, large data sets. And yeah, that's a very interesting thing about these formal methods. So how do you go about when you want to develop a probabilistic notion of causation, of causal relations? The first basic idea that you need is that instead of talking about invariable associations like Hume did, we talk about probabilistic correlation. What is correlation? Well, we say that two events A and B are positively correlated if and only if the conditional probability of A given B is larger than the unconditional probability of A. So you could say it like this: the presence of B raises the probability of A. For example, if A is developing lung cancer and B is smoking, the probability of getting lung cancer, given that someone is a smoker, is higher than the probability of the unconditional probability of a person getting a lung cancer. So that's why we say that smoking and lung cancer are positively correlated. This expression here is just one of many possible ways to express positive correlation between A and B, and all these ways of expressing positive correlation are equivalent. They are equivalent more or less. They are clearly equivalent when neither the probability of A nor the probability of B are 0 or 1. So, so they are equivalent, except that some of them are just not well defined for one or two of these cases. Yeah. Okay, so the probability of A given B is larger than the probability of A alone, if and only if the probability of B given A is larger than the probability of B. You can easily see this if you calculate the probability of A and B once from these two terms and one from these two terms, and then compare the equations. And so you can pause the video and try this out, or you can just trust me that so of course positive correlation would be symmetric. Yeah, if A is positively correlated with B, then B is positively correlated with A. It's also the case that you can, instead of saying this, you can also say probability of A given B is larger than probability of A given non-B. Or the probability of B given A is larger than the probability of B given non-A. This is all equivalent. This is the case exactly when this is the case, except in cases when one of the probabilities is not well defined. And lastly, you can also say the probability of A and B is larger than the probability of A times the probability of B, which you can see from the fact that this is the case, that this is also a way of articulating this. You can see that this inequality here is just this inequality divided by the probability of B. Yeah. And because probability of B is a positive number, the inequality, those are then or those are equivalent. Or for cases where probability of B is a positive number, that is when it's larger than 0, those are then equivalent. So I wanted you to, I went over this a little bit because in different texts you find different of these. Different authors pick one or the other to articulate what they mean by positive correlation. This one is, of course, the nicest because these probabilities are always well defined. We say that A and B are negatively correlated if and only if the probability of A given B is smaller than probability of A. So having teeth, medical problems with your teeth is negatively correlated with brushing your teeth regularly, for example. And if A and B are either positively or negatively correlated, we just say that they are correlated or probabilistically correlated. So, so probabilistic correlation, the idea that we're talking about probabilistic correlation instead of invariable association, that takes care of the problem that causes are not always invariably followed by certain kinds of events. For example, the smoking causes lung cancer example. It's clear how we now can talk about this, and it also promises to deal with indeterminism because we can apply the concept of probabilistic correlation also um, to indeterministic phenomena. But in and by itself, the probabilistic correlation alone does nothing to take care of spurious correlations. So the the mercury column in my barometer and the storms will be probabilistically correlated, but still I don't want to say that one is the cause of the other. So um, some people say that, okay, if you want to do this, if you want to um, sort and distinguish the real causal correlations the from the spurious correlations, you need experiment and intervention. Only experiment and intervention can help to sort this out. This is sort of the traditional methodological approach, but the the entire project that I'm going to talk about today is one that says, well, maybe not. Maybe we can do better than that. Maybe we can sort out the true causal correlations from the data, from looking at the correlations, the probabilistic regularities alone, without having to intervene. Like if you introduce intervention, then that would not be a pure regularity account anymore. And to do this, you need some more basic ideas. The second basic idea you need is that you can somehow sort um, and distinguish the real causal probabilistic correlations from the merely apparent ones, like the barometer and storm correlation, by means of Reichenbach's screening off condition. What is that? So Hans Reichenbach, or an idea following Hans Reichenbach from his posthumous book, The Direction of Time from the 1950s, is for A to be a probabilistic cause of B, two things have to be given, namely one, probabilistic correlation condition and a no screening off condition, which I've called PC for probabilistic correlation. So A and B are probabilistically correlated. And in addition to this, you also need to see no screening off condition fulfilled. There is no earlier factor that screens B off from A. And now screening off is defined as conditional probabilistic independence. So X screens B off from A if and only if the probability of B given A and X is the same as the probability of B given X alone. And this is sometimes written like here, like this. So Bx is screening B off from A. Or in other words, B and A are probabilistically independent given X. Now, so the idea is unconditionally, A and B are probabilistically correlated, so they are not probabilistically independent. So B given A, probability of B given A is certainly different from the probability, the unconditional probability of B. But if you fix X, there is an X such as if you fix X, so if you view everything conditional on X, then the correlation between A and B disappears. That's the idea. So, for example, X in the cases of the barometer and the storm is a sudden drop in atmospheric pressure. So, because the sudden drop in atmospheric pressure is the cause of both the barometer reading and the storm. So, if you look at just the barometer reading and the storm, the probability of getting a storm, given that you have a drop in the barometer reading is higher than the unconditional probability of getting a storm. But if you view everything given that there is a sudden drop in atmospheric pressure, then the probability of getting a storm given a drop in the mercury column and a sudden drop in atmospheric pressure is no different from the probability of getting a storm just given the drop in atmospheric pressure. The the barometer reading seems relevant if you just look at barometer reading and the storm, but it becomes irrelevant if you start considering atmospheric pressure. So let me give another example because this is an important concept for everything that follows. So think of B as giving birth and A as having been wearing maternity clothes for the past weeks. So these two are clearly probabilistically correlated. The probability that a person gives birth, given that they have been wearing maternity clothes for the past few weeks, is higher than the unconditional probability of a person giving birth. But there's a factor X that screens off the correlation, and that is, of course, the factor being pregnant. Yeah. So if you fix pregnancy and you look only at cases where the person is pregnant, then the correlation between birth and wearing maternity clothes disappears. Given that someone is pregnant, the probability that she gives birth, given that she has been wearing maternity clothes for the past weeks and she's pregnant, is no different from the probability of her giving birth, given that she's pregnant alone. So, okay. So the idea is that real causal probabilistic correlations are the ones that can't be screened off, that where you don't find any other condition that screens off this condition, screens off the correlation. But if you just look at this like this, there seems to be a limitation. And the limitation is that the screening off condition alone, if you just look at isolated variables, does not help to uniquely identify causal relations, I should have said, unless the temporal sequence of factors is already independently known. And if we have data sets, for example, we can't assume that we always know the temporal sequence of factors. For example, given this structure of correlations, some of which are screened off. So you have three factors, A, B, and C, and they are all correlated with each other. Yeah. But C screens off the correlation between A and B. Whereas the correlation between A and C is not screened off, and the correlation between C and B is not screened off. We can't from this thing alone, it's not clear whether the causal order is this or this or this, because um, com well, complete common causes will screen off correlations. If C describes everything that together causes A and B, then we can expect C to screen off any correlation between A and B. So the correlation can be expected to disappear if we fix C. But does so will complete causal intermediaries. So if all the causal connection between A and B goes through C, then we also expect C to screen off the correlation between A and B. And this can be in this direction or in this direction. So just by looking at isolated variables and seeing that one screens off certain correlations is still leaving lots of things undetermined. And hence, the third and final basic idea that we need to start with the approach that I want to talk about today is the idea to not look at isolated variables, but to consider the entire wider structure of factors. So look at how other factors around A, B, and C are correlated with them, and then use that information to see whether we cannot find a uniquely determined um, causal order. So A, B, and C will typically not stand alone. There will be a host of other factors that stand in correlations with them, some screened off by yet other factors, some not. And this is the kind of information that we need to settle the question of what cause-effect relations really are between them. So that's the basic idea for an approach that has been called causal modeling, and that has also been called Bayes nets. And the strategy of the approach is roughly like this. Basically use the idea of probabilistic correlation and also the idea that no screening off is important for genuine um, correlations, and combine this with the assumption that the causal direction is the predominant direction of open bifurcations. So we predominantly have common cause structure, where one causal factor um, causes several others. And so the idea that the condition that screens off a correlation is the the condition that is the causally earlier one. So that is on the cause side, not on the effect side. And this, you realize this basic approach by embedding all these ideas in a system of conditions that together determine when a directed acyclic graph of factors, that is of variables, can be accepted as a causal structure. So this may seem obscure, but I'm going to explain it in a moment. So you take a data set, a set of variables, and there are lots and lots of correlations between these data, and then you could, in principle, draw all kinds of graphs over the variables. I'm going to explain in a moment what these are. And then you say, okay, let's define a set of nice conditions that sorts out those graphs that represent acceptable causal structures from the others that cannot be interpreted as causal structures. And which are these? Well, we use these ideas here. Correlation, no screening off. Direction is the predominant the open bifurcations um, indicate the direction of causality. So work on this project was begun by statisticians in the 1970s, and then Judah Pearl, an Israeli American computer scientist, started to describe many properties of networks such as these in the late 1980s. And Pearl also coined the term Bayes networks because of the fact that the probabilities involved often only make sense as degree of belief type probabilities. Some of them also make sense as frequencies, but at least some usually don't. And the input information in these nets is often at least partly subjective. So he used the term Bayes nets. He also used Bayesian updating in connection with his work on these networks, which is an aspect that doesn't concern us today. But well, he introduced the word Bayes nets, though it's not. This is not the connection between this and Bayesianism is not strong, I would say. Um, but he has introduced the term, and the term somehow stuck. The alternative name that you can use is causal modeling. And then this is one of his best known books and the complete treatment of this approach from the year 2000. But as I said, his work on this began in the 1980s. Then also three philosophers of science, namely Peter Spires, Clark Glimmer, and Richard Scheinis, have contributed a lot to this work, starting in the early 1990s, and they connected Bayes nets with experimental interventions. Um, that's sort of their take on this, and this is another very important treatment of causal modeling. A very standard treatment by Spires, Glimmer, and Chinese. Interesting for us, of course, and because they are philosophers of science. We've encountered Clark Glimmer before. He was the one who brought the problem of old evidence um, onto the agenda of the discussion of Bayesianism in philosophy of science. So, okay. Um, how does this work, and what the hell are directed acyclic graphs? This is not a very complicated idea. We start from a set of variables. V is a set of variables. And then intuitively, G is a directed acyclic graph over V if and only if G consists of a web of connections that have a direction and that each connect two of the variables, as can be represented by arrows, in such a way that there is no uninterrupted chain of arrows that forms a closed loop. That's the acyclic part. So this is a directed acyclic graph over this set of variables. So we have a set of these letters represent variables, and a directed acyclic graph is just a set of arrows that where you without closed loops. Yeah. So this is not a directed acyclic graph because it contains a closed loop here. So the idea is if you have a set of variables, then a large number of different such graphs, different directed acyclic graphs or DAGs, could in principle be constructed over this set. A very large number. And now the idea is let's articulate precise conditions on the probabilistic correlations between the variables to identify the kinds of graphs that are permissible as structures representing causal relations. So the probabilistic correlations between the variables determine which of these graphs represent candidates for causal structures. And of course, we want a condition that incorporates all these ideas, correlation, but no screening off, and so on. So the crucial condition in the whole theory that does the work is called the Markov condition. It was already named by those statisticians who started the early work on this in the 1970s, and arguably it should better have been called the Reichenbach condition, but let's be that as it may. The name is firmly established. It's called the Markov condition, and the Markov condition looks like this. It's okay. It's not a complicated. It looks complicated at the first sight, but it's really not a complicated idea. So for all x and for all y, these are of course the quantification over the variables in the set v. Yeah, we have a set of variables v, and we quantify over the variables. So if y is not a descendant of x, then the parents of x screen off x from y. So in this formula, descendants x indicates the set of all direct and indirect descendants of x in the graph G. So, for example, D is a descendant of B, but F is also a descendant of B, and J is also a descendant of B. Yeah, everything that you can reach from B by following arrows is a descendant. Parents, on the other hand, is a set of parents, and that means just the immediate parents. So, for example, the set consisting just of C and D is the set of parents of F. Yeah? B is not a parent of F because only the immediate parents count. So you also see that here, this is then basically, this is a term that indicates a set, but it appears here in a position where we would expect a proposition. And what we mean is the conjunction of the elements of this set. So, and we also talk, so this is a probability expression. Yeah, it means that the probability of x given y and parent x is no different from the probability of x given parent x alone. But x and y are variables. We don't talk about the probabilities of variables. This is not something that we have defined. I mean, the probability of someone getting lung cancer given that they smoke, that's something that we can talk about. But the probability of lung cancer given smoking, where smoking is a variable which can either be yes or no, or perhaps can take a value of how many cigarettes per day, that's not something that is defined. So what we mean by talking about the probability of variables is we should understand this statement as quantified over a suitable range of variables. So for variables, for all these possible values that the variable can take, is always screened off. They're always screened off like this. It's complicated. It's better to leave this like this for the moment, and not only for the moment, but for the rest of the lecture. I'm not going to go into this. It's so for a range of relevant and interesting values that these variables can take, the screening off relation should hold. So that's the thing. I want to re-articulate the Markov condition in prose to make it better comprehensible. So what the Markov condition says is that the parents of a variable jointly screen it off from all other variables except its descendants. And again, it's best to look at this with respect to an example. So here we have a set of variables, A, B, C, D, E, F, and this is a graph, a DAG, a directed acyclic graph. And what the Markov condition now says is that this graph is only acceptable if the following independencies, if these independencies all hold. A, so the parents of A must screen off A from all other variables except its descendants. The parent of A is just C. Yeah? So C must screen off A both from B and from D. Not from F or E because those are the descendants and that's okay. But C must screen off A from both from B and from D. B must also be screened off by its parents, but the B now has two parents, so they must jointly, C and D, screen off B from all other variables except its descendants. So all other variables except E. B must be screened off from A and F, that is, jointly by C and D. C must be unconditionally independent from D because C and D don't have parents. So C must be screened off by the empty set. From just from D because D is the only other variable that's not a descendant of C. And so on. D also must be screened off by the empty set, must be unconditionally independent from all other variables except its descendants. And so on for E and for F. You can pause the video and look at it if you understand whether this is exactly what the Markov condition implies. Now, if you change the direction of one arrow, this arrow, for example, then the Markov condition demands a different set of independencies. Yeah? And I do this also in particular to show that how this now helps, because we have this situation with A, B, and C, the one that we had before. Yeah. So there's a correlation. So C screens off the correlation between A and B. Yeah. But we don't know. I mean, if you're just looking at C, A, B, and C, that's all we know, and then we can't decide. Because in this structure, also, C screens off the correlation between A and B. Yeah, because A must be screened off by its parents from all other variables except its descendants. That includes also B. But in addition to this information, we have other kinds of screening of relations, and they are different from this situation. So we can distinguish these kinds of information. For example, in this situation, where C is a causal intermediary between A and B, B must also be screened off from F. By A. And okay, it also must be screened off from A here. Sorry, here, I'm sorry, B must not be screened off from F because B is a descendant of because F is a descendant from B, whereas here B must be screened off from F by C and D. here, but not here. So the set of screening of relations that must hold differs in both cases. Sorry, let me do this again because this was a bit confused. So for this graph here to be acceptable as a causal structure, Markov condition demands that B must be screened off from F by C and D jointly. For this graph, not. I mean, also here, B must be screened off from F by A, because A is a parent of F in both cases. So here. But B here need not be screened off from F by C and D jointly. Or to point out another difference between the two graphs, here C and D must be unconditionally independent. Whereas here, C and D must be, the correlation between C and D must be screened off by B, because B is a parent of C. So there are differences in the kind of independencies that are demanded by the Markov conditions for the different structures, and these differences can be used to distinguish one from the other, and they're only generated by the larger, wider structure of variables as they hang together. That's how the thing is supposed to work. Note that the Markov condition only works if the set of variables that we consider is in a certain sense complete and contains everything that we need. In particular, it will break down if there are common causes to different elements in the set of variables that are themselves not included in the set of variables. That will lead to problems. For example, consider that this is the situation. We have a set of variables including smoking, yellow fingers, and red hair, but there's also, unbeknownst to us, an unknown gene that is causally responsible both for red hair and for yellow fingers. Yeah. Then, if that's so, we will find yellow fingers and red hair correlated amongst our variables. And the problem is, so the only thing that we should have when we don't know this, when we don't have this, the only thing that we should have is this arrow, smoking as being responsible for yellow fingers, albeit not alone. But the graph over V, if this single arrow is a graph, does not satisfy the Markov condition, because there is a correlation between yellow fingers and red hair, and that it should be screened off by the parents of yellow fingers, which is just this variable, but it doesn't. Now, this correlation is not screened off by this, and therefore this wouldn't satisfy the Markov condition. And the reason for this is, and the Markov condition will force us to include additional arrows to satisfy the Markov condition here and or here or whatever, and those arrows don't really make any sense. So the Markov condition will lead to intuitively wrong results if we don't have, if the set of variables is not closed with respect to common causes. That's a limitation, or something that you definitely have to keep in mind. The Markov condition is central and crucial, but it's not alone. It's not enough considered alone. Um, Nothing about the Markov condition prevents us from inserting additional arrows. Yeah. So once you have a structure that satisfies the Markov condition, adding extra um, arrows will not do any harm. So, for example, this example, yeah, A, B, and C are mutually correlated, and C screens off the correlation between A and B. Markov condition is satisfied in this graph, um, but it's also satisfied in this graph. No problem, because so the yeah because it's still it will still be satisfied here. Um, so we need to make additional stipulations. We need a condition that somehow requires us to not choose just any structure that satisfies the Markov condition, but somehow choose the most parsimonious graph that satisfies the Markov condition. And so there are several possibilities for this, and the most common is the faithfulness condition, the so-called faithfulness condition. And the faithfulness condition is simply that every conditional or unconditional independence between two variables must be required by the Markov conditions. So there should not be any variables that are just happen to be conditionally independent of each other, even though the Markov condition does not explicitly demand it. In our example, in the example that we just give, this structure, so our stipulation is that C screens off A from B, but if we have this structure, Markov condition doesn't demand that C must screen A from B because B is amongst A's descendants, and B does not have to be screened off from anything because it doesn't have any descendants, and all the other variables are jointly its parents. So whereas here this is explicitly demanded that B is screened off from A by C, and yeah. So therefore, the faithfulness condition helps us to exclude this. This is not okay because not all the independencies that exist in the variables are demanded by the Markov condition. We take only every conditional or unconditional independence must be required by the Markov condition. This is one of the ways what you can do. There's a weaker alternative, the so-called minimality condition. So that's the condition that no subgraph of the graph meets the Markov condition. And yeah, so if faithfulness and Markov imply minimality, but not the other way around. In the remainder today's lecture, I would like to touch upon some interesting problems for this approach. So I hope to have illustrated that this is an interesting approach that you can achieve quite a lot by fairly simple conditions. And so this actually is a quite successful approach, not only in theory, but also in practice. And you have modules for causal modeling, for example, now in standard statistic software packages like SPSS, and it's a very successful program. But there are some problems, especially from the philosophical point of view, uh, as there always are. Um, One really interesting problem is the so-called Simpson's paradox, when probabilistic influences cancel each other out. I have called this, and it's the Simpson's paradox can best be explained by means of an example. So suppose we have some condition, medical condition, a very uh, grave condition, high mortality, but there's a treatment, and that its treatment is somewhat beneficial, but not terribly much. And I've doctored these numbers in such a way that um, two effects exactly cancel each other out, or in a way, it's three effects, namely that um, the the sex of the um, of the patients, and whether they receive the treatment or don't receive the treatment. Um, and so the way that these numbers work is you can see, so if you look at the men, among the treated men, then we have a mortality of 38%, and among the untreated, we have a slightly higher mortality, namely 43%. Among the treated women, of which there are more, so there are more women altogether, but also more treated when the proportion of treated women is higher. You can make up your own reason for this. Perhaps the treatment just does not um, cannot be used in certain cases. Um, it's also the same, but the mortality is higher than generally. But still, also for women, the mortality for the treated women is lower than for the untreated women. So the treatment is beneficial. The group of treated persons has a um, lower mortality both for women and for men. But now, interestingly, if you look at the combined numbers of men and women, the effect of the treatment effect seems to disappear. So we have altogether in the we have 12 treated women who survived and 8 treated men who survived. And but we have 15 treated women who died and 5 treated men who died. So that's exactly 50% um, of the treated people died, and exactly 50% of the untreated people also died, because if you add these together, there are 6. So um, this is possible. Just I mean, yeah, okay. The numbers illustrate that this is possible intuitively a little bit. This is possible because of the different base mortality in women and men, and because of the different numbers. So there are more women with generally have a higher mortality for this disease included in our numbers, and therefore it they end up it end up it ends up canceling each other out. So these effects are possible, and this is called Simpson's paradox. Sometimes, unfortunately, the word Simpson's paradox is sometimes also used for another thing, which is so-called reversal of inequalities problem. So you can have it's slightly similar, but where you can have where when you look at total numbers, you even get a reversal of the effect. For example, that more seems, yeah. Um, but this is what I mean by when I say Simpson's paradox. The problem that um, the probabilities cancel each other. The probabilistic effects exactly cancel each other out. And why is this a problem? Okay, okay. Intuitively, if you look at the variables sex, treatment, and mortality, um, this seems right. Sex determines or co-determines mortality with treatment. Sex also seems to play an influence in treatment because the proportion of treated uh, um, is higher in women than in men. But that should be that those should be the causal influences. But if you look at the numbers, the only graph that is permitted by both Markov condition and faithfulness condition is this. This would be a graph where the sex is co-determined by treatment and mortality. Um, why is this? Because these numbers mean that from a probabilistic point of view, treatment and mortality are unconditionally not correlated. They are conditionally correlated. They're correlated condition on women and they're correlated condition on sex, but they're unconditionally not correlated. And if they are unconditionally not correlated, um, then faithfulness condition um, together with the Markov condition demands that this is the only structure that is allowed. Um, so for these cases, the causal modeling approach seems to deliver wrong results. One response that has been given by Spirides, Glimmer, and Shinies is that the set of points in the parameter space in which the exact deletion of probabilistic correlation occurs has Lebesgue measure 0, meaning this is infinitely improbable. That's what they say. It's infinitely improbable to occur, that they exactly cancel each other out. And if there's only a slight, so the problem disappears from the perspective of causal modeling if there's if just a slight tiny bit of difference between the mortalities, then again we have correlation and no problem. And only if it cancels each other out exactly, and this to happen um, is basically infinitely improbable. That's what they say. In contrast, Nancy Cartwright, for example, has pointed out that in many practically relevant situations, we might be dealing with systems that are potentially designed to extinguish correlations, and therefore this is not infinitely improbable, and there could be actually reasons why um, uh, exact canceling each other out could happen. In any case, it is definitely a problem for, so it may not be, so Spiri's, Glimmer, and Shiny's response is perhaps most satisfying as response to potential practical concerns. Say, oh, this result could give us incorrect conclusions. But for philosophical concerns, if you look at causal modeling actually as a program in the probabilistic approach to causation, say, that would mean that, okay, we can pick out these kind of graphs from the network of correlations of things in the world, and that's what causation is. That's what causation is. The graphs that are picked out by the Markov condition and the faithful condition. That's basically what one way of approaching the probabilistic theory of causation would look like. Then that would be weird. In this examples like this would be weird, because then what the only thing you could say is, so it might be very improbable, but in cases, in possible worlds, it seems to be possible, yeah, in possible world where this actually happens, that is actually the causation. That is the causal structure. And then if that happens, that means, yes, that sex is caused by treatment and mortality. Weird. Not acceptable. So, be that as it may, I want to touch upon other problems. Again, it's just a selection of problems, but these are some that just really some that I find interesting in this case. Yeah. Another is it's more a practical problem now. It's the problem of the selection of population, because you always have data just about some particular population, and this problem indicates that selection of the population may artificially create problems for this approach. For example, you have a population that consists of hospital patients, so you have an increased presence of some disease D. Yeah. Unknown to us, B and A jointly promote D. Because in this hospital population, there are more people that suffer from this disease, far more than in the general population. Within and they are so within this population, B and A will be positively correlated, because the B and A cases are brought into this subpopulation, the hospital population, because of D. D selects them for inclusion in our population. And then they will be positively correlated. The assumption is that they are not positively correlated in the general population. A and B don't cause each other, and they don't have common causes. But in our subpopulation, they will be positively correlated. And the Markov condition working on data from our subpopulation will then exclude the correct causal graph, which is a causal graph where A and B jointly contribute to D causally, because um, there's a non-screened off correlation between A and B, and that would then have to be somehow explained by some arrows, and yeah, that seems unfortunate, or a really potential practical problem for the application of these methods. And lastly, there may be correlations without a common cause, and there may be there may be spurious correlations without a common cause. I should really correct this slide. So the whole program of causal modeling is based on this idea that that it's able to deal with the problem of spurious correlations by attributing them all to common causes. Yeah? And by saying, okay, look, there appears to be this correlation, but we can sort this out because it's screened off by this other variable, which is a common cause. But if there are perhaps spurious correlations in the world that are not that don't have a common cause, but that just are just so there, then that would create a problem, because there would be no X to screen off these correlations. And Elliot Sober, who's brought up this problem his example was the bread prices in England and the sea level in Venice. Both are rising all the time, basically. And but is there a common cause for this? But there seems to be a correlation, which is presumably clearly a spurious correlation. And if you are looking for more examples, you can look to so there's this there's this guy named Tyler Vegan who has created a website with spurious correlations. What he does is he's tapping on different data sets and he's just looking for correlations. And if you have enough data sets, then you find some correlations. For example, between for the available data between 2000 and 2009, the divorce rate in Maine correlates with per capita consumption of margarine. It correlates quite nicely, as you can see. Or also worldwide non-commercial space launches correlates with sociology doctorates awarded for all the available data that Tyler Vegan looked at between 1997 and 2009. So presumably this correlation is it's there. It's just so there. And of course you might say, well, we just have to wait a little longer and you will see that at some point the correlation will not continue to hold. But what if it does? What if it does? And we don't have any there presumably there's no common cause. There's no variable that screens off these variables from each other. And yeah, if these cases, so that's both the practical. I would submit that's both a potential practical problem, depending on how often these kinds of things can be found in real data sets, and a theoretical problem if you take this serious as an analysis of what causation is, then you would somehow have to say, well, there must be a causal structure responsible for this in this probabilistic approach. All right. So that's it for today. That's it. What I wanted to say about causes and correlations and this very interesting approach and these very interesting formal methods that have been developed in order to deal with it. And I look forward to talking to you about this soon. Goodbye.